Hello, I'm going to go over our last two pages of the fill in the blank kinetics lecture notes. So right now we're talking about chain growth polymerization kinetics, and we want to be able to figure out what's the average length of the chain. So we did this for step growth polymerizations, and all we needed was the extent of reaction. So we derived an expression for the number average degree of polymerization as a function of extent of reaction, and you might not remember, but it's just the number average degree of polymerization equals 1 over 1 minus p, and p is the extent of reaction. And when we did this, everything was included: monomers, trimers, dimers, but we don't want to do that for chain growth polymerizations because we have all kinds of monomers, right? Most of our reaction vessel is monomer that's just sitting around doing nothing. And then we have grown chains and chains that are growing. So all we want to think about is the chains that are growing or have already grown. So we define a new term, the kinetic chain length. Okay? So the kinetic chain length is the average number of monomers polymerized per chain radical or cation or anion at a particular instant in time during the polymerization. What? Okay, so it sounds complicated, but it really isn't. So let's plug in some numbers. At time t, 100 chains have been started and 1 million monomers have been polymerized. What's the average chain length? What's the kinetic chain length? We just need to take that 1 million monomers that have been polymerized and divide by the number of chains that were started. And in this case, we get some very long chains, 10,000 repeat units. Okay? So this is a useful term, right? We don't want to put our monomers into the average because it would bring down the average a lot because there's a lot of monomer left over. So at short times, the kinetic chain length is equal to the rate of propagation divided by the rate of initiation. So the rate of propagation divided by the rate of initiation. And this is valid at short times. At really long times, it gets messy. So usually when we're asking about the kinetic chain length, we're asking about the initial kinetic chain length. Okay. So we can very quickly take this and substitute in RP and RI. And where is that page? Here we go. So RP and RI. Okay, so if I do that, I go ahead and do that. So my rate of propagation over my rate of initiation equals Kp radical concentration times the monomer concentration. Again, this is just for the free radical. And then we have Ri, which is 2F Kd times the initiator concentration. If we had an anionic or a cationic polymerization, we just use those rate laws instead of the ones for free radical. Now, what do we do here? We know Kp, F, Kd, those are things that we could look up. We would know our initial monomer concentration and our initial initiator concentration, but we don't know this. So we need to make our standard steady state assumption and substitute in for the concentration of radicals. So think about it. What is that steady state assumption? Our radical concentration is at steady state. Therefore, the rate of initiation has to equal the rate of termination. So I'll do that quickly. FKD, D times D times the initiator concentration equals 2KT times the radical concentration squared. That means the radical concentration equals FKD initiator concentration divided by KT. So if I plug that in here, right, and simplify my reaction. Okay, simplify my equation. I'm going to skip some steps, but you should go figure out that algebra because we want to simplify it. So it's Kp times the monomer concentration, because see this FKD, oops, what did I forget? The 1/2 power. This FKD is going to divide into this one, okay? So we end up with 2 FKD, actually KT, to the 1/2 power times the initiator concentration to the 1/2 power. Okay, so that is our kinetic chain length. So let's look. Our rate of polymerization was proportional to the monomer concentration times the initiator concentration to the 1/2. So if we want our polymerization to go faster, we could increase the monomer concentration, or we could increase the initiator concentration. Hopefully that makes sense, right? If you want it to polymerize faster, you add more initiator. Now here, if we add more initiator, what happens? The length of the chain goes down, right? Because it's the monomer concentration divided by the initiator concentration to the 1/2. So if we start more chains, our average length of chain is going to be shorter. So I hope that makes sense to all of you. Okay. Now, so we define this term, this kinetic chain length. And again, it's defined in terms of the average number of monomers polymerized per chain radical or anion or cation. Now, for free radical polymerizations, we have 2 termination mechanisms, and that impacts how the kinetic chain length relates to our number average degree of polymerization. Okay, so let's think about this. How does the kinetic chain length relate to the degree of polymerization? And again, this is for free radical. If termination is by disproportionation, the average molecular weight doesn't change, right? It's just the number average degree of polymerization and the kinetic chain length are the same. If termination is by combination, what happens? We have 2 chains come together and form a single chain. So now it's 2 times the kinetic chain length. So this is important to remember and to understand. I won't give you these relationships because you should be able to think about it and figure it out. Now note, for anionic and cationic polymerizations, the kinetic chain length and the number average degree of polymerization are the same. Okay. But in the special case of free radical, we have this termination by combination, and so sometimes it's double the kinetic chain length. Now, experimentally, termination usually occurs through both mechanisms, and usually not in equal proportion. So to account for this, we're going to define a new parameter, which is, I think it's a Greek letter. I call it squiggle, C or something like that, but anyway, I call it squiggle. So squiggle is the number of dead chains formed per termination. So the rate of dead chain formation over the rate of termination. And you can look at this in the book and go through those equations. But let's start with this. So the rate of dead chain formation is the same as the disappearance of chain radicals. So it's the decrease in concentration of the radicals that are on the chain. That rate law is here. So the squiggle is going to be the relationship, the ratio of those two. This over the rate of termination. The radical concentration squared drops out. KTD plus KTC is just KT. So you can write it as KT, or you can leave it this way. So what is the number average degree of polymerization equal? It's 2V divided by squiggle. So the number average degree of polymerization is 2 times the kinetic chain length divided by squiggle. Okay. Oh, okay. So if you need this equation, you can always look it up. But let's look at the limits of it, okay? So let's think about when KTC is much, much greater than KTD. Much, much greater. So now we have the number average degree of polymerization equals 2V. So we've got KTC is much greater than KTD. So now if we just simplify that, it's KTC over KTC. 1. That cancels. So if termination by combination is much bigger, we've got 2V. Now let's look at if KTD is much, much greater than KTC. So the number average degree of polymerization, 2V times 2 times the kinetic chain length equals, in this case, KTD is much bigger, so KTD over 2 KTD. And that ends up being approximately equal to the kinetic chain length. Okay? Which is just what we said at the top of the page. So this all works out. Okay? So that is the kinetic chain length. And again, this is really useful because one of the things we want to know, often what we want to know is our initial rate of polymerization, which is equal to our initial rate of propagation, and what's the initial chain length. And so we use the kinetic chain length to determine our initial number average degree of polymerization, and those relationships are right here for free radical polymerization. And again, this is true for anionic and cationic. Okay, and that is our final page of our fill-in-the-blank lecture notes. The other thing I wanted to show you is some other rate laws. Okay, so here are step growth rate laws. Here's rate laws for anionic, cationic, the free radical rate laws we've been using, and there's even free radical rate laws when you have a thermal generation of radicals. No added initiator. You raise the temperature and the radicals form on their own. Okay, so there's many different types of rate laws. So why don't we very quickly figure out, let's look at the anionic rate laws. So for the anionic, that's what we're going to look at right now. So what is the rate of polymerization equal to? And then we can look at what is the kinetic chain length. So the rate of polymerization equals the rate of propagation, which equals Kp times the anion concentration times the monomer concentration. Okay, so I need to get rid of the anion concentration. So let's do the steady state assumption. Ri equals RT. So Ki, initiator concentration to the 1/2 times the monomer concentration equals KTR, termination by is done by transfer, so that's why it's TR, times the anion concentration times the solvent concentration in this case. Okay, so the anion concentration is simply Ki, initiator concentration to the 1/2 monomer concentration divided by KTR and the solvent concentration. All I need to do is take that and plug it in. So my rate of propagation simply equals Ki, Kp, initiator to the 1/2 monomer concentration squared divided by rate constant for termination and the solvent concentration. Okay, so that's how we get to our rate of polymerization. So then what is the kinetic chain length? We just learned what the kinetic chain length was. Kinetic chain length is RP over RI equals RP over RI. Okay. So we've calculated our anion concentration, so we could just do RP over RI and plug that in, no problem. I'm going to do the steady state assumption a slightly different way. I'm going to do RP over RT, the rate of propagation over the rate of termination. Now I'm going to plug that in. Okay, so I have right here Kp times the anion concentration times the monomer concentration divided by KT, KTR, by the RT, the rate of termination, KTR, anion concentration times the solvent concentration. That cancels. So now I have my kinetic chain length, Kp times the monomer concentration over KTR over the solvent concentration. So there we go. There's the kinetic chain length, and there's our rate of polymerization. And if the question asks for the initial rate of polymerization or the initial kinetic chain length, you don't have to separate the variables and integrate. You just plug in the initial concentrations, okay, and go from there, okay? We'll talk a little bit more about problem solving when we start going over some of the problems in the problem set, okay? Thank you.